Now we are going to study electric potential due to a charged conductor. So if you have a conductor, and it is positively charged, it has a total charge of plus Q. Then let us see what is the potential at any point on the surface and any point inside the surface at any other point. So let us say you're moving from this point to this point, and let us say it is A. You're moving from A to B and from B to C. As is known that electric field inside a conductor is zero. So if we have to find out the potential difference, so between B and A, it will be VB minus VA integral of E vector dot ds vector will be equal to 0. So it means that potential at A will be equal to potential at B. In a similar manner, when we are moving from B to C, now at B, the electric field will be along this direction, and ds vector, because you're moving from here to here, so at each point ds vector will be tangent, so at this point it will be like this, and electric field will be like this. So electric field and displacement vector, it will always make an angle of 90 degrees. So E vector dot ds vector when we are moving from B to C will be equal to E ds cosine of 90. So it will be equal to 0. So when we integrate it over from B to C, what we'll get is Vc minus Vb will be equal to integral B to C E vector dot ds vector should be equal to 0. So we can say that Vc is equal to Vb. Now let us find out what will be the potential at any point outside the conductor. Now let us say that this point is any point D. So in order to find the potential at D, let us first of all see what is the electric field at D. So let us try to find out. Now because it is a charged conductor, if you draw a Gaussian surface at this point around this sphere, charged sphere, you'll see that the electric field and the area vector, they will be in the same direction. So by Gauss's law, E vector dot dA vector will be the charge enclosed upon epsilon naught. Now in this Gaussian surface, the charge enclosed is plus Q. So we'll have plus Q upon epsilon naught. And electric field is uniform on this surface, and the angle between them is 0. So it will be EdA integral and cosine of 0. So it will be the total area 4 pi r square will be equal to Q upon epsilon naught, which implies that electric field will be Q upon 4 pi epsilon naught r square at that point. So if you know the electric field, you can find out what is the potential at that point. So it will be Vd minus V infinity will be equal to minus integral of infinity to d E vector dot ds vector. Now what we're doing here is, because whenever we find potential difference, it is with respect to some point. So it means that suppose that we are coming from an infinite point to this point. We are coming from infinity to d. So the potential at infinity and potential at d. Okay. So final minus initial Vd minus V infinity will be equal to final initial to final E vector dot ds vector. This will be the potential difference between these two points. So now the displacement is along the radial vector. We are moving along the radius, so this expression could also be written as infinity to d E d r, and they are along the same direction. Okay, so you know that the potential at infinity will be 0. So Vd will be equal to, now electric field will be Ke, because you know this is Ke upon r square dr, integral from infinity to d. So it will be Ke r minus 2 plus 1 minus 2 plus 1 infinity to d. So it could also be written as Keq, we missed a negative sign, so it will be 1 upon rd minus 1 upon infinity. So the potential at d will be Keq upon rd. Okay, so now what is rd? Rd will be this distance, the distance from the center to this point d. It will be rd. So now if suppose that we are talking about the surface of the conductor. Now the surface, let us say that the radius of the surface of the conductor is r. So the potential at this point on the surface of the conductor will be given by, when rd is equal to r, the potential difference on the surface of the conductor will be Keq upon capital R. Okay, so this potential will be equal to, because Vb is on the surface, point C is on the surface. Okay, now what does this mean in conclusion? If we have to conclude all this information, it means that if there is a conductor and there is some point inside, there is some point on the surface, there is some point outside the surface. Okay, so let us say this point is A, this point is B, and this point is C. So the potential at C will be Keq upon the distance RC, and at B, potential at B will be Keq upon R if this distance is capital R of the conductor. And because the potential at B is equal to potential at C, because the electric field inside is 0, as we have proved in the last page, so we can say that the potential B is equal to A. So we can say that the potential at A will be Keq upon R. Now this is a very important point. It means that inside a conductor the potential is constant. So if on all of this conductor the potential will be constant. So if it is some potential V here, it will be V here, it will be V here, it will be V here. Everywhere it will be constant until you reach here. And after that it will change with the radius, with the distance. As the distance will increase, the potential will decrease. So if I have to plot this with potential versus small r, then this is capital R. So the potential will have a constant value, which will be KEQ upon R when it is inside the radius, inside the conductor and on the conductor. And as you move away, it will decrease with R. So potential will be given by KEQ upon R. It will decrease with R. Now let us try to understand what is the behavior of a conductor when it has a cavity. Okay, so a cavity within a conductor. A cavity means we are having a hollow surface. Now suppose we are having a shell, let us say it is a shell, and it is spherical shell. Okay, and suppose it has some thickness. Let me just give it some thickness. Okay, so this is a shell. So because it is a conductor, so this is a conductor, and it is hollow, and there is no charge inside the conductor. There is no charge inside the conductor, while on this conductor perhaps maybe it is positively charged, plus Q. It has on it some charge plus Q. Now as you all know that inside the conductor the electric field is 0. Okay, so suppose that now you want to move from this point to this point. Okay, so let us say it is point A and this is point B. Now so VB minus VA will be equal to integral of E vector dot ds vector. Now because it is a conductor, so it should have same potential, as you've learned from here that in a conductor, from here we conclude that in a conductor potential will remain constant everywhere. Okay, so suppose if you have any conductor, there is a wire and it is joined by some wire. So if this is at V, it will also be at V. Okay, this is what it means. If it is a conductor, conductor and conductor, then it will be the same potential. So if it is a conductor, it means that VB must be equal to VA. So this implies that the electric field will be 0. Okay, so everywhere inside this cavity the electric field will be 0. And you might move from any other path, so inside the electric field will be 0. There is another way of looking at it, and that is by Gauss's law also, like we have done in the last chapter, that if you draw a Gaussian surface, okay, if there is no charge inside, then electric field will be equal to 0. Okay, so then we can also explain it by this, that if it is a cavity, electric field will be 0, and so it means that if something is surrounded by a metal, inside it will have an electric field of 0.